rather than coming once and running away and never come back forever. So thank you, Martin, for coming again. And Martin has two hats on as a representative of Waters, but also nonlinear dynamics, which is kind of the same thing still, but only relatively recently the same thing. And he's going to talk to you a bit about label-free quantification using Proteomics QI.
Okay, thank you very much, Ben, for the introduction and for inviting me back again. It's a pleasure to be here, and it's good to see so many people attending this. It's really good. I think it's a fantastic event, so make the most of it as you can. So today I've got quite a few slides. We're going to skip through fairly quickly. Looking at label-free quantitation using ion abundance. Progenesis QI is the software that we've developed. It's a commercial software package. A little bit of background for those who have never heard of Progenesis at all. There might be a few of you in here. Nonlinear Dynamics is the company behind the Progenesis brand of software. We've been developing this since 1989, and the company was acquired by Waters in August 2013, so 2 years ago this month. Okay. We are still developing the software, it's still the same team. We're based in Newcastle, which is roughly there in the northeast of England, where you might have heard of the Tyne Bridge before, which is very similar in design to the Sydney Harbour Bridge, because it was the original, and then they used that and scaled it up to go across Sydney, and that's the building that we're based in. So we have been acquired by Waters, we're part of Waters, but as always, Progenesis was developed to support data from any instrument. So for those of you who haven't got a Waters machine, don't switch off, because you can still accept any data from any instrument without any file conversion. So any instrumentation, if you want to do label-free, comparative quant, then again, we can handle data directly from any instrumentation. It's mainly, as Bruno's expressed this morning, it's a relative or comparative analysis. We want to compare, there are different responses to different peptides, and we want to look at the relative response of a specific peptide in different situations or different groups. So it's a comparative or relative quant. A lot of it is for discovery, protein expression, modification changes. And what we're doing when we say ion abundance, what we're doing is we're modelling, this is just showing obviously the C12 peak here, we're modelling the area, both in mass and retention time, to give a three-dimensional volume of each of these isotopic peaks, and then we're adding those peaks together to give the total volume of the ion envelope. And we do that consistently across any number of files to then compare the data. There are other ways of doing it. So again, spectral counting is one way. So in this talk, I'm not just going to talk about the way we do it. I'm trying to cover some of the challenges, the pitfalls, and identify. So there are spectral counting methods, which again, if you want to have a quick overview of some of the high abundant proteins in the data, could be a very appropriate choice to go through. If you want to look down and look at some of the lower abundant things to get more precision, then MS1 precursor intensity or peak-based quantification methods are going to be more appropriate for that sort of comparative quant. And you can also look at some of the MS2 sun intensity. All of these slides I will provide on a PDF, so again, some of the references don't bother scribbling down. I'll provide PDF copies of the presentation. So these are just some of the typical analysis steps, not necessarily all in this order, depending on the programs and the way these analysis is being performed. But to give you through, we have some processing, alignment, detection. We then go into this peptide or feature quantification. We try to, from that, there'll be some normalization typically performed at this level. We then try to, from that, infer protein quantification from all of these measures. There'll be some statistical analysis, either at both or various points. Identification workflows going off at a tangent to actually annotate these ions or these signals that we're measuring. And then finally inferring that and trying to now, much more, this is a focus that we're working on at the moment, putting all of these lists of proteins into some biological context. So I'll expand on that. So if we take through the initial steps, signal pre-processing. Typical LC-MS files, I'm sure some of you who've already acquired and run some data will realise they are typically large and can be very large. Different vendors and different companies have different ways of trying to reduce the file size and make life easier for processing. Some of it, one approach might be centroiding the data. Our preference is not to have it centroided because it makes it a lot harder to distinguish features and characteristics from that data set, so we prefer to have it in profile mode. But centroiding can dramatically reduce the amount of data. There are other methods, wavelet filtering, again, can reduce the file size while retaining profile information. that's the actual one we prefer. We integrate that into our program. And also at this point in pre-processing, a lot of tools will do some sort of background subtraction and denoising of the data. You may have some systems where they have a threshold. Certain signals below a certain level are not recorded, or there's some initial pre-processing. There is quite a lot of debate about what is raw data, what is pre-processing, what is post-processing, because some of it is actually done on the fly on the machine. So some of these steps, be aware whether the data you're acquiring off the instrument has already been pre-processed. If you're running on an FTICR, I should assure you, you don't want to be pre-processing the data any further. It has been very highly pre-processed. If you're running on other platforms, then there's a big variation in how much of that pre-processing has already occurred on the raw data. So the alignment. Alignments can occur either at this step, so in our workflow we align up front. Some programs would use some sort of identification information to alignment, so it may appear in different parts of the workflow. So what we're doing in alignment, we're trying to make comparisons between runs. So therefore, this is a screenshot it's a review, it's an automatic process, it's just a screenshot to show you what the algorithm has done. But you've got color coding, we can look at the whole area, color coded, some areas are green, they're already well aligned, some areas are amber or red, poor alignment, and in those areas you can overlay, here's just overlay two files on top, we've got retention time and M/Z. And most of these features, you can see that the pink feature here is eluting earlier than its corresponding green feature off the adjacent file. So again, the way we use on this is pattern recognition. It doesn't need any upfront information. It doesn't need fragmentation data. It doesn't need identification. It's just looking for patterns of MS1. If your LC is running stably and the chemistries of your column are running consistently, then things should be eluting in the same sequence order. If they elute in the same sequence order, then they will create a very, very complex pattern of thousands of constellations or features. And we can use that pattern to pull things together. So, there are different methods. Some of them use feature data, some of them use identification, some of them use additional properties. Depending on instrumentation, we may use drift time if drift time is also available. So as well as the retention time, there are some data formats, there are additional properties that we can use to align and identify that it is the same feature across the different runs. And again, depending on the method of alignment, it may fit in different places in the workflow. So post-alignment, hopefully you'll find that, again, we will give scores to, again, quality. If you're looking, we've mentioned a few times, in label-free quantification, reproducibility, robustness is important. It is important, therefore, to monitor the quality of the data as you go through the processing. So again, in this software, you'll see all sorts of different, what we call QC metrics or QC measures as you go through the software. Feature detection and deconvolution. Again, peak detection corresponds to peptide ion signals. So again, we've got a map. This is our retention times, M/Z, and these are all of the different features across the entire project or experiment. A lot of them, variety of models and settings. Again, most software allows some sort of user intervention to determine how sensitive, how far into the data do you want to detect. It may be that you just want to take a quick pass and have a look at some of the higher abundant peptides, infer from those, or it may be you want to do a really detailed proteomic investigation and go down as low as you can into the noise, or as close as you can towards the noise, to pick out the smallest feature possible, depending on what you're trying to accomplish. Again, there are all sorts of different characteristics of an isotope. Obviously there's charge we can use, and again, it's very easy to determine the charge of a feature, and we can determine that. In high resolution systems, a lot of things are interwoven, and again, one of the reasons why we measure each isotope individually, and then sum of those intensities together to give the total volume, is because lots of other things can be incorporated within them, or interwoven within the same feature. So again, it allows us to measure and quantify individual isotopes, and another isotope that is interwoven isn't interfering with the quantification. Okay. So some of the challenges on this, variation in detection across samples and feature matching. One of the biggest problems in a lot of this is if you want to make comparisons, you want to be making sure you're comparing the same thing across all of your runs. And a big challenge of that, and a big problem of that, is when you have missing values, where you either haven't detected a number of reasons why it might be missing, and maybe it's not present, biologically, you've knocked it out, it isn't there. It could be it's present, but it's below whatever limits of detection or thresholds that have been set on the system, or physical limits of detection of the system. And then there are also the other situation where it might be present, but for whatever reason it's been misaligned, misdetected, hasn't been identified, some sort of error along the process of assumptions. But from a comparative analysis, missing values they create a big problem from an informatics perspective. If we want to make these comparisons and use a lot of multivariate stats and different tools to analyze the data, typically in a lot of proteomics data sets, if you aren't accounting for those, you can find that very quickly when you run even to 3-4 replicates, you can have large numbers of missing data. And by large numbers, you can be pushing up to 50% of your data set is full of zeros or missing values. And that becomes a major problem. So how do we, and again, different references on here, we can look at those. So how do we accommodate this? There are different ways. So one of the ways, notably on this, we could impute. So reasonable for the misalignments, but its sensor generally absent all their values, so imputing them. We could remove observations. So again, a lot of you, if you are using multivariate stats, you may be using a tool at the moment where there is a requirement of it to be matched in X number of features. So you've run 5 replicates, and your assumption is you only select features where it's present in 3 out of the 5. In other words, you're throwing away all the rest of the observations because they don't meet the criteria. Another one is interpolate, model, try to go back to the features that you have measured and see if you can model from those the missing values. Or alternatively, and the one that, again, that we take within software, is to rely on accurate alignment of the data, combine what we call co-detection or cross-detection, and try to model in the exact location of where the isotope is across every file, and measure the signal and or noise, whatever is detectable at that exact location, so that again, we're not trying to define signal to noise in the actual detection process, we're just modelling the location and measuring whatever signal is coming from that location, and then allowing the statistical analysis to determine what if a change is significant or not. So, one slide, again, this is the, really this is probably one bit of major IP in Progenesis technology as to how we go back and how do we detect things in a slightly different way to try and address this problem of missing data. So here I've got these very cartoon schematics for attention time, M/Z, 2 files from the blue group, 2 files from this orangey red group. And if I wanted to make comparative quant, if I ran detection independently on this file, I would detect these 4 features. That's straightforward. And I go to this file and I do independent detection, and I find 4 features. And after you've done that, you then start making comparisons. And you can compare the 3 things that are common, and the things that are different, well, what does that compare to? There's nothing to be detected. And likewise, what does this one compare to? How do I make a comparison if I can't detect it? That's the problem with missing data. So the way we address this in the software is we have already aligned things that are common. So these things that are common are in exactly the same place on every file. What we then do is we start to, in memory, model another file. And we start to model every single isotope. So we go through this file, we find every isotope location, and we model the locations into memory. And we go through file 2, file 3, file 4, and we model in the location of every single isotope across the entire project, or experiment. Once you've got that, and we've got that built, then we can run the detection algorithm at the experimental level, define the location of every ion, every isotope in the whole project, and then those can be modelled back onto every single raw file. So this is an approach of how we then would get a measurement and how we would address the issue of missing data. So you will then have a measurement, it may be noise, it may be 0, it will be a measurement. It allows us to then determine the effect size, get a reliable measure of variance for every feature across every group, and determine the effect size between the different groups and calculate statistical power for each feature. In reality, if you look at this is some examples, so I've got here, I've got a feature from 3 replicates from this purple group, where we can see C12, C plus 1 plus 2, and you have nice, as you'd expect, isotopic distribution, which is used for the detection algorithm. When you go to the other group, you'll see that this one we can just about see a few scans from the C13. This one, the only thing detectable is the C12, which for a lot of independent detection algorithms start to struggle. And then you get to this point where you've only got a couple of scans hitting C12, and there's not even an elution profile, a clear elution profile. But we can still measure it, the feature's still there. So it does drive down detection sensitivity as well. But the most important thing, it gives us a like-for-like comparison. It means that the precision of measurement, because we're measuring over exactly the same window, the same number of isotopes, we're comparing things in exactly like-for-like manner. We're not comparing 2 isotopes on one file with 3 isotopes on another, etc. So this is going through, that's the feature detection. We then come on to peptide quantification and normalization. Normalization. You are running an experiment, you're trying to control your method as well as possible, but there's always going to be some variation in the amount of sample you will load onto the column. That is what normalization is trying to adjust for. If you've loaded 10% more sample onto your column, then in theory, if a lot of your peptides and proteins are expected to be there at 1-to-1 levels, instead of seeing 1-to-1 in your ratios, you expect to see if you've loaded 10% more, all your ratios will be 10% higher. It'll be 1 to 1. Okay. So what does normalization do? It's trying to adjust for that on-column load or that bias that's been introduced from loading. There are a number of assumptions. One of them I just mentioned there, that most ions are expected to be unchanged. They're expected to be there at 1-to-1 ratios, unaffected by the experimental condition. So you can normalize the total ion current. That's been used for a long time. If the TIC changes, then maybe you've loaded more sample. Fair assumption. There are some areas, if anyone's working on plant proteomics, where you've got some very, very high abundant proteins in there that may be changing under response to stress. It can really upset the normalization because the TIC all of a sudden can change significantly when those proteins change. So there are outliers. Another method is to calculate the ratios. If you look at ratios, so if you take every single ion and we scatter plot them, then in theory it should have a nice normal distribution, and in theory they should all be at ratios of 1-to-1. So we put it in log space, we determine where the mean is, and then we determine the offset, so we can tell that it's 15% more sample load. It's automatic, you can review the graphs, it'll show you what the variation is in your load. The green bars just indicate, flag the outliers, flag the major differences. So it's really trying to accommodate that error in loading of the column, or technical variance in how much sample you loaded, on the assumption that things are common. There are other alternatives. Again, we can use, we've looked at things like variance stabilization normalization, VSN, it's a technique, we've looked at that, regression-based, all sorts of different methods. In the software itself, there are defaults, because the default assumes lots of things aren't changing. If that isn't valid, then there are other alternatives in the software. You might want to just switch it off and take your pipetting is extremely, your sample prep is very robust and you know you've loaded exactly the same amount. That might be valid. You might want to normalize to a subset of housekeeping peptides or proteins that you can hypothesize, or you have other evidence to show that this subset of features are definitely stable and not affected by the experimental condition. Or you might want to spike something in and normalize to those. So there are different strategies, and they're available there, depending on the application and the particular experimental design. Identification. So once we've got all these features, label-free quant, again, we need to go off and identify. I'm not going to go into the details. Our approach on this is there are lots of different search engines out there. We're not going to reinvent another search engine. We're just about tools to allow you to plug in and use whichever search engine. So we've already had a great talk already on Mascot and search engines in general, how they work. So again, different rules and different ways that we can then interact, export files to those search engines and import results back directly from those search engines. So again, choose the search engine of choice. One of the things we do have in the software, though, is this challenge of trying to identify as many features as possible. One of the challenges in proteomics is that you'll measure a large number of features, you'll have a slightly smaller number of features that are fragmented, and of those you'll have an even smaller number of features that have actually been identified. And when you look at it and you step back and you take a global look at your results and the fact that all of your protein results are based on this small subset, sometimes it makes you step back and realise all of your interpretations, you've reduced it from all this data you originally acquired, you've reduced it down to this small subset. So how can we increase this identification so that we can get better sequence coverage and get more reliable data, hopefully more reliable by increasing this range? There are different strategies, different ways of doing it. Again, there can be inclusion lists, exclusion lists, fractionation as a good way of enriching certain low abundant things and to get a better signal to noise by increasing the on-column concentration. And again, ion mobility separation is another way of trying to enhance the separation. again, if that's an option you have available. So again, there are different ways, we can have iterative ways of importing and keep accumulating more IDs to gradually build this up. There are lots of different approaches for most of these. Again, from this DDA, fast DDA, HD DDA, faster DDA, it's all DDA in slightly different versions. And again, you've got different versions of DIA, various different files and formats. Some of them, you might have various bespoke informatic solutions, so that if you're working with MSE, then you have to work within PLGS platform. Some of them are more open, so again, depending on the platform you're using, it's going to probably more dictate which method on there and which search engines you're restricted to or not. In general, in our software, we're trying to link this, as I said, to external databases and just import and export as required. So it's really an option that's flexibility versus convenience. Okay. Protein quantification. How do we infer a protein? Different methods. One of the things we can use and we do use within our software is we take the fact that actually in every single run, if we've got 3 peptides, we have measured the same through the code detection, we've measured exactly the same 3 peptides in exactly the same way on every single file. So rather than looking at averages or means of the ratios and things, we can actually simply sum up the raw data and sum up the abundance of these peptides for run 1, likewise for every other run, and then we can do all the stats again at the protein level based on the summed intensities. Okay, it's one of the benefits of using the code detection. How do we infer that? When we look at a protein, we have what we call conflict identifications. Okay, so you might have, again, the same sequence has come from 2 different proteins. If that's the case in the software, by default, we don't know what the ratio is between those 2, so by default, we wouldn't use it for quantification. It'll still show you there in sequence coverage that potentially we've found this sequence, but we wouldn't use it for quantification because it could have come, it might be 50-50 or 70-30, we've got no idea what the ratio is between the 2 proteins. The other time we get a lot of conflicts is where you have different spectra. One spectra says, I know the sequence is X, and then on a different run, another spectra comes out, it may be noisier or cleaner, and says, I know the spectra, it's Y. And then that creates a conflict. Which is the correct? If both of them have good valid scores, then again, which one is the correct identification? In those situations, again, unless you can manually resolve things like that, we wouldn't default it, don't use it unless it can be resolved. We do have things, and it was mentioned, parsimony grouping, again, so again, if we've got different isoforms where all of the features could be from 2 different proteins, then again, we would group the proteins. And again, when you look at all the peptides and a protein, so these are just 2 views on here. If I'm looking at a protein here, I've got a number of 10, 12 different peptides, and again, nice, clear that all of the peptides are in agreement, consensus, they're all showing a downregulation in this group compared to this group. That's nice, straightforward. And if only everything was straightforward and as easy as that, it would be nice. In reality, when you look at this is another protein here. We've got a number of 20-odd peptides, some of which are unique, some are not. At the moment I have highlighted on here, this is showing all peptides. It is just showing that the impact of some non-unique peptides intermixed with unique peptides. And it's why we always select unique peptides, because you will have interference from other peptides which are shared or coming from other proteins. So again, default is to use peptides which are unique. If we look at, again, PTMs, there's some great talks on PTMs. This is looking at unique peptides from a protein, and again, inferring what is the protein inferred to the protein level. So we can see here, the general consensus is that most of all these peptide ions and these peptides are showing a downregulation in this group C compared to group A, with the exception of 2 different ions which are actually both from the same peptide. The reason that is that this one is a modification, it's a phosphopeptide. Yes, so there is a drop in the abundance of the protein, but it doesn't mean that this phosphopeptide is dropping. Okay? So remember, you might have some activation and abundance in the same. So when you take an overview, again, some of these, a lot of these, you may need to review the data and check the data to see whether all the peptides, is that reflecting the abundance change in the protein, or is it reflecting some of the activation or modification of PTMs within the data? And finally, on this absolute quantification or precision quantification, I think absolute has been adopted But again, in analytical chemistry, it isn't. We're not calibrating to an individual standard. So I follow what Bruno was saying earlier about using the term absolute with caution. It's an approximation. If you look at some of the CVs on this, if you're getting within 20%, it's fairly good on some of these from a label-free perspective. There are different ways of doing it. You've got Apex using scale spectral counting techniques. You've got NPI, which is using precursor to proportional possibilities, and you've got some intensity-based IVAC ones. The one that we typically use in the software is this one using Hi3, where we're taking the 3 most abundant peptides per protein and use their average abundance as an escalator. So again, for a protein, the assumption is that within a protein there will be 3 peptides that will fly well. If we look at the abundance of those 3 peptides, then there is very good correlation between the sum of those, or the average of those abundance, and the protein abundance. There are a couple of things. Again, there are assumptions on here that their molar amount is equivalent across proteins within the system, such that, again, that is an approximation. This is where the accuracy comes into question in this sort of technique. But again, from this paper, Silver's paper, again, you see there is some quite good correlations of this Hi3 approach across there. I'll say there is one other thing on this Hi3 that we have. Again, you can use it calibrated, and you can use it to get an approximate concentration of an individual protein, which is quite good. But also, even if without spiking in and doing that, you can get a stoichiometry. You can look at the ratio. If you apply Hi3 even without calibration, the abundance of protein A then allows you to compare that to the stoichiometry and the abundance of protein B. So you start to get some idea. You can start to put proteins in some sort of order based on their dynamic range, and start to see, okay, within this matrix, which are my lower abundant proteins and which are my higher abundant proteins, and see where they fit in that range, in that dynamic range. So that's just taking the Hi3 without calibration. So on that, statistics, we'll skip through some of these. Changes of interest, p-values, student t-test, fold chains, all sorts of assumptions, normality. The one thing I would say on this, there's a lot of false discovery rates, a lot of things that we're going to look at. We use a technique called Q-values. Again, it comes from a microarray. The assumption is that if we had no change with our normal distribution, we could again assess this null factor. If we took a typical distribution, we've got one distribution here, which is the null factor, and then we've got another distribution on top. So what we can do is, by setting a Q-value cutoff, we can work out what proportion of your discoveries fit into this null factor below the dotted red line, and which proportion fit above. Power analysis is a great way of trying to work. One of the common things we get dealing with fold change. A lot of you say, well, what fold change should I use? What p-value cutoff should I use? Power and power calculations is a very good way of looking at the effect size, because it will take into account the variance within a group as well as the effect between the two groups. So again, the probability that a given effect would be detected as a rejection of the null hypothesis, i.e. you're right outside, you're well away from this other distribution. So there is a good introduction article, Carpenter paper there, again, if you want to have a look at that. And again, it's something that we report. Quality control I mentioned before, principal component analysis. I know it's a lot of stats and it's 3 o'clock, okay, but it is one of the best quality control tools you could have. Before you start digging into your data and finding things with a low p-value or something significant, I could have a data set where there's absolutely nothing changing whatsoever, and I'll still have proteins with a low p-value, because they are there by random chance. Okay? Step back and have a look at your data, have a look at something like the PCA analysis, and see, can you see your experimental design? So on here on this study, I've got 5 different groups, and I can see the biggest difference is this group is different to that group. These groups are very similar, but there are some more subtle changes between them. So there's all sorts of questions I can now ask of the data to try and tease out which proteins are responsible for those observations. It's great if you see things clustering in your groups into your experimental design. Fantastic. QC, we have a lot of QC in the data, whether it be from your triptych digest, whether it be from your LC performance, whether it be from your mass spec resolution on that data set. It is important in label-free to quality control at different stages. So if you're seeing all of a sudden you've got a massive increase in the number of triptych digests, single digests, on here, miscleavages, indication that the trypsin isn't working efficiently. If we see that all of a sudden the resolution is an example, I've got very good mass precision, plus or minus 3-4 ppm, except all of a sudden all my masses that are there in terms of their true values are minus 5 ppm offset from 0. So we know that the calibration machine is off by 5 ppm. So you know that if you're running your searches, why you might be missing a whole load of identifications off one end of your... So again, recalibration, instrumentation. Finally, putting all this into pathway tools, we have interfaces directly into a number of commercial tools, Ingenuity being the main one, and again there are lots of other freeware, Impala, Panther are two that we're integrated with. The reason we've integrated with some of those is because they will allow that Impala will allow incorporation of not just proteomic data, but other omics meta streams as well, so metabolomics data, and then you can model all of that onto pathway tools and use those provided tools. So again, we're not trying to reinvent it, we're just trying to find convenient ways for you to take this data set, load it into a pathway tool, and to see, rather than looking at proteins individually in a great big long list, take a wider view of the broad picture and see put that into biological context. So with that, I'd like to thank you very much for your time, thank you for listening, and happy to take any questions.